Chapter 11 is a continuation of Chapter 10 on the topic of energy. We're specifically going to look at how a system can gain or lose energy. We will see when a system's energy is conserved and discuss the role of friction in all of this. We will go back to the energy model and include the possibility for the system to gain or lose energy when it's interacting with the environment, and that's where the concept of work is going to come in. We will specifically define what work is and look at some examples of that. And then we will talk about the energy equation. At that point we will have all the pieces we need, and we will put them together, and we will consider separate cases when the external work done is zero or when there's no friction. So let's go back to the basic energy model. And we have previously talked about the kinetic energy, the potential energies, both in the case of gravitational and elastic potential energy. We mentioned but did not discuss in great detail thermal energy. But the important thing now is that we will consider situations where the system is interacting with the environment, and that interaction will be described by what we will refer to as the work. When work is positive, that would imply that energy has been added to the system, and when the work is negative, that's when energy has been removed from the system. At that point, we will look at the full accounting of energy by including the thermal energy as well as the work done by the external forces. So we will have a complete equation for the change of the energy of the system, which include the changes in its kinetic energy, the changes in its potential energies, both gravitational and elastic, and the changes in its thermal energy. And then we will look specifically at cases when the energy can be transferred in and out of the system. That's when the W on the right hand side will be some number not equal to zero. And then in some cases we will consider the system to be isolated when it's not interacting with anything, in which case the W, the work done by the external forces, will be zero, and we will say then that the energy of the system will be conserved. Let's talk now about the work done by a force, and for the moment we will focus our attention on constant forces. We will deal with the non-constant forces in a separate video that will be posted later. So first thing, the word work has a very specific meaning in physics, so you'll have to be very careful in using it. It will actually represent the energy transferred in and out of a system by the application of external forces. And in this picture here, what we see is a pitcher throwing a baseball. In this case, the pitcher is adding kinetic energy to the ball by doing work. That is, by pushing the ball with his arm, he's performing some work. So the mathematical definition of the work done by a constant force can be visualized here. So what we're looking at here is a force F, which is shown here in red, that is acting on, let's say, a point-like object that is moving from an initial position SI, moving all along a straight line here, and going to a final position SF. The S is just for a generic position. It can be X, Y in any possible direction. The force F makes an angle theta with respect to the direction of motion, and what is defined as the work done by the force is the product of the magnitude of the force F multiplied by the displacement delta R, that is the distance along the direction of motion, delta R, from the initial position to the final position, and then the cosine of the angle between the force and the direction of motion, the angle that's shown here. So another way we can look at this is to talk about the component of the force F sub s along the direction of motion. That would be, by using trigonometry and looking at this triangle here, that would be the magnitude of the force multiplied by the cosine of theta, and that would be the component of the force in the direction of delta R. So we can think of it in two different ways, but essentially it'll boil down again to the product of magnitude of the force times displacement times the cosine of the angle. Looking at the units, we can see that the unit of work are Newton meter, which is eventually reduced to joules, just like the units of energy. Here's a quick example of how we would use this definition. So here we have a rope that is pulling a suitcase at a 45-degree angle. The tension applied by the rope is 20 Newton, and the question is, how much work does this tension do if we pull the suitcase 100 meters? So here's a quick description of the problem. The position of the suitcase changes along the horizontal, in this case, by 100 meters, so we will call the displacement simply delta x. The magnitude of force is described in the problem as 20 newtons, and the angle theta here is 45 degrees, so it's a straightforward application of the definition. 20 newtons times 100 meters times 45 degrees, cosine of 45 degrees. That gives you 1400 joules of work done by the person or whoever or whatever machine is pulling this suitcase. So one of the things that will happen very often is we will get products of force times displacement with angles, and so as you can see, when the angle is equal to 0, like in this picture here, the force is in red, the displacement is in blue, so the object or the particle is moving from left to right, and in this case the angle is 0, so the cosine of 0 being 1, the work done is simply the product F times delta R, and we end up with a positive number, and so energy is being added to the system. In the second case here, the force makes an angle theta, but the angle is an acute angle, that is less than 90 degrees, and so the cosine of that is going to be positive, even though the cosine is going to be less than 1, but it's still going to be positive. Then the product is going to be F times delta R times cosine theta, and we'll still end up with positive work, which means that energy has been added to the system. When the displacement, that's again the arrow in blue here, is perpendicular to the force, or the force is perpendicular to the displacement, then the angle between those two is 90, and the cosine of that is 0, and no work has been done, and there's no transfer of energy to the system. Finally, if the force and the displacement make an angle, obtuse angle, that is more than 90 degrees, then the cosine will be a negative number, and we will then get negative work done, which means that energy has been transferred out of the system. The extreme case would be this one here at the bottom of the picture, where the force is directly opposite the displacement, in which case the angle is 180 degrees, and the cosine of that is exactly negative 1, and that product F times delta R will give us the magnitude of the work, but we get a negative number in this case. Now that we have talked about work, let's focus on the concept of thermal energy, which is actually a special application of this idea of work to the case of friction, and that is the only one that we will be interested in here, and specifically it's actually kinetic friction. So as discussed in the previous video, when two objects slide against each other, at the atomic level there are some interactions between the atoms of one object versus the atoms of the other object, and kinetic energy is transferred to both objects on both sides of the separation or the divide, like here. This will be the top object, this will be the bottom object, and there is a transfer of kinetic energy into thermal energy, meaning that the temperature on both sides of that interface is going to increase, and so we talk about here a dissipative force because some of the kinetic energy has been dissipated into thermal energy. Here at the microscopic level, that is the case that we will be interested in most of the time, we can represent this way. Imagine that we have a box that is sliding on a rough surface, and we pull it to the right with a tension T, a rope that's pulling on the block, and we show here the friction force, which is opposite the direction of motion. And we imagine that the box is moving to the right with a constant velocity, although constant velocity is not really necessary here. But we will talk about the increase in thermal energy for the whole system, the system being the block, the surface, and Earth. So the thermal energy of the system will increase by an amount that will be the product of the magnitude of the force, that would be the positive number, just the magnitude of the force, multiplied by the delta S, which represents the displacement, the horizontal displacement in this case, of the box as it slides from left to right. And this number is always going to be a positive number. Dissipated forces always increase the thermal energy, they never decrease it. Here's a quick example of how this would be applied. So in this example, a rope pulls a 10 kilogram wooden crate 3 meters across a wood floor. And the question is, what is a change in thermal energy? To be able to answer that question, we need to know something about the kinetic friction, and the coefficient here is mentioned to be 0.2. So the setup is essentially the one that you saw in the previous picture. We need to know something about the friction force. As discussed before, the friction force would be the coefficient of friction multiplied by the normal force. The normal force will, in this case, be equal to mg, since the box is sliding horizontally, and so the friction force will just be mu k times m times g. So the thermal energy, using the equation we mentioned a moment ago, will be the product of all these terms, and with these numbers it comes out to be 59 joules. So in this case we would say that the thermal energy of the system made of the crate and the floor has increased by 59 joules. We can't tell where the 59 joules went, whether it's all in the crate or all in the floor or a little bit of both. That's fine, we don't need to know that. We just need to know that the system has gained 59 joules. Let's go back now to the idea of conservation of energy. So when a system is interacting with the outside world, there will be work done by the external forces, and that's going to cause some changes in the energy of the system. The energy of the system is made of kinetic energy, potential energy, and thermal energy, or we can also group that into mechanical energy and thermal energy. And anytime an object or a system is interacting with the outside world, there can be some changes in the energy of the system, and that's when we will consider the idea of conservation of energy. So when the system is interacting with the outside world, we need to know whether the work done is positive or negative. When the work done is positive, energy has been added into the system. When the work done is negative, energy has been removed from the system. Within the system itself, there can be some changes, a modification of energy from kinetic to potential. We've already talked about that. Or, as we now have discussed, also a transformation of energy from, let's say, kinetic or potential into thermal energy. Okay, so this will represent that the fact that the energy of the system has changed because of external forces acting on the system, but there are also some possible changes within the system itself. If the system does not interact with the outside world, so now the W external is equal to 0, then the energy of the system will not change, and this is what this equation in the middle says here. The change in the energy of the system is equal to 0. So this will be a particular case when the system is not interacting with the outside world. Then we can say that the energy of the system is conserved. Before looking at the applications and especially the problems, as we will see in class, let me go back and review some of the terms that have been used so far. So we've talked about kinetic and potential energies, both gravitational and elastic. We've now introduced the concept of energy dissipated by friction, and that is what this E sub th is referring to. Mechanical energy is a combination of kinetic and potential energy, whether it's gravitational or elastic doesn't make any difference. And so when we talk about the energy of the system, we talk about the combination of all these energies: kinetic, gravitational potential energy, elastic potential energy, and thermal energy. Sometimes we group together the kinetic and potential energies, and we refer to those two as mechanical energy. So we can now talk about the energy of the system as being mechanical and thermal energy. So a system can be a non-dissipative system. That means that there is no friction, and so the change in thermal energy is equal to 0. If the system is dissipative, meaning it has some friction, then the change in thermal energy is not equal to 0, and we'll have to account for that. The change in thermal energy is always positive, and we'll have to keep that in mind. A system can also be isolated, meaning it does not interact with the outside environment, in which case the work done by the external forces is equal to 0. And if it's not isolated, then the system is interacting, and in this case the work done by the external forces is not equal to 0. So many combinations are possible, and here I think 4. Okay. So a system can be non-dissipative and isolated. That means it has no friction, and so the delta E sub pH, thermal energy change, is equal to 0, and the work done by the external forces is equal to 0. So in this case, there is a change, possibly a change in kinetic and a change in potential energy of the system, but the combination of the two changes is equal to 0. That's when we talk about conservation of mechanical energy. Those are the examples that we discuss in Chapter 10. The system can also be non-dissipative but not isolated, meaning there's no friction, therefore there is no change in thermal energy, but there is work done by the external forces, and so the sum of the changes of kinetic and potential energy is equal to the work done by the external forces. If the system is dissipative now, if there is friction, but is isolated, that is, no external force, then the change in thermal energy is not equal to 0, but the work done by the external forces is equal to 0, and the change in the energy of the system is actually equal to 0. The kinetic energy can change, the potential energy can change, the thermal energy can change, but the combination of all those changes is equal to 0, and in this case we can talk about conservation of energy for the system. Finally, in the most general case, when the system is dissipative, there is friction, and it's not isolated, there are some external forces acting on the system, then the change in kinetic energy plus the change in potential energy plus the change in thermal energy will equal the work done by the external forces in this case. One important reminder, when we talk about the work done by external forces, we do not include gravity, the spring force, or the friction force. Those three forces have already been accounted for by the inclusion of something called gravitational potential energy. The spring force has been accounted for by the inclusion of the elastic potential energy, and the friction force is tied to the change in thermal energy. So whenever we talk about work done by external forces, you should exclude these three forces. Do not include those three in the work done by external forces. Finally, let's look at the energy bar charts. So in the most general case, we'll be looking at the change in kinetic energy, potential energy, and possibly thermal energy with the application of some external force. And so we can also write down that energy that I mentioned before this way. So here we are counting together the initial energies, kinetic and potential. Potential can include both gravitational and elastic. Then we add to this the work done by the external forces, which can be positive or negative, and that will result in a final amount of energy, kinetic and potential. But here we also add the change in thermal energy. So notice here we did not put in the initial amount of thermal energy, we simply keep the difference, the change in thermal energy, on the right hand side of this equation. So graphically, here's what the energy bar chart may look like. So here in green we have some initial kinetic energy, we have some initial potential energy, and in this particular example the work done by the external forces happens to be negative, so you notice that the bar goes below the 0. And at the end we have some kinetic energy. We seem to have more in this example than we had before. The potential energy is all gone, as you can see here, and then there's some increase in the thermal energy. This is just a generic example, it's not meant to be very specific, but it shows that the work done comes in right here between the energies from the system, kinetic and potential, and before we add this we look at the final energies, kinetic and potential and thermal energy. The work would be included right here. Here are a couple of examples. So here we're looking at a speeding car that skids to a halt, and we are to show the energy transfers and energy transformation on an energy bar chart. So here's what a bar chart looks like. The car has initially some kinetic energy, so we would show it with a green bar that goes up this way. This is the initial state. So the car is presumably moving on a horizontal line, so we don't have to worry about the potential energy. It's also not being affected by any kind of external force. Remember, we do not include friction, gravity, or spring forces in the work done. And at the end, the car has stopped completely, so its kinetic energy will be 0. Its potential energy will also be 0. But all the energy that the car had is gone into thermal energy. Obviously, by the skidding of the car on the road, there's been a lot of transfer of energy to thermal energy, and so the bar on the far right here shows the amount of energy transferred being equal to the amount of energy that we had initially in the system, which was kinetic energy of the system. Here's a second example. So this one talks about a rope that's lifting a box at a constant speed, and we have to show the energy transfer in this case. So if the box is moving at a constant speed, that means it has kinetic energy, but it's constant, so the final kinetic energy would be equal. There is work done by the rope. In this case, the rope is pulling the box up, so we will have some positive contribution from the external force, and that work is going to increase the potential energy of the box because the box has gone up, and as it goes up it has gained potential energy, so the system has increased its potential energy. But conservation of energy requires that all of the energies plus the work done should be equal to the final energy. So if you count the bars on the bar chart, you get 1 bar up here plus 3 here, and that's equal to 1 here plus 3 here. So overall we have a balanced equation for the energy of the system and the external work done by the external forces.